In this lecture, I'm going to walk you through the basics of fitting linear models, simple linear models, using Stan and the front end for Stan BRMS. I'm assuming that you have read chapters 1 to 3, or you will read chapters 1 to 3 at some point before watching this lecture or after watching this lecture. The textbook is of course available here. The source code is available at this GitHub repository, and if you want to buy a physical copy of the book, you can do that here. So just to quickly remind you of the central ideas behind linear modeling, we are going to assume here that we have some continuous data, which I'm calling y, and this data is a vector, it's in vector form, and we are assuming that the data are independent and they're coming from the same distribution. So what we say in statistics is that we assume that the data are IID, independent and identically distributed. This IID term is assumed whenever I draw this tilde, right? So what I'm saying here is that I'm assuming that the data are independent and identically distributed, and they're coming from a normal random variable which has defined for it some unknown mu and sigma parameters. Okay, so that's what this statement means here. So that's the kind of data we want to model. And this, so what you're looking at here is a statistical model, right? This is already statistical modeling here. And you can rewrite this in a slightly different form, but it's an identical statement. So what we are saying in this line here is that the data, the vector of y values, is coming from a linear model where there is some mean mu, right, that represents the mean value of that dependent variable. Let's call it reading times or something, and there is some random variation around that mean that's represented by this residual term epsilon, and the epsilon is coming from a normal distribution with mean 0 and standard deviation sigma. So the basic approach that we are going to adopt when doing data analysis and statistical modeling in the Bayesian framework is that we're going to start by specifying a likelihood function. In this case, I'm assuming a likelihood function that is the normal, right? But I could have chosen some other likelihood function. We will choose a likelihood function. We will define then a prior on the parameter or parameters. In this case, there are two parameters, mu and sigma. So we're going to define two priors for those. And then we will try to figure out whether the model, which consists of the likelihood and the prior specifications, gives us sensible data. If we produce data from that model, that will be the prior predictive distribution. These are called prior predictive checks. And once we have fit the model to the data, we will also check whether the model produces future data that are reasonable, given what we have already observed in the data that we have. So those are called posterior predictive checks. So prior predictive and posterior predictive checks will be an important part of modeling when we work on analyzing data. In all cases, the end goal for us will be to determine the marginal posterior distributions of the parameters of interest. For example, in this case, we have mu and sigma as the parameters. So the end result of our data analysis will be to produce a posterior distribution for mu and a posterior distribution for sigma. So these are the marginal distributions of each of those parameters coming from a joint posterior distribution for mu and sigma. So it's underlyingly a bivariate distribution of posteriors. The posterior is a bivariate underlyingly, but we are drawing out the marginal distributions like we did in chapter 1 for mu and sigma. Okay, and all this, determining the posterior distributions for mu and sigma will be done using software instead of, analytical calculations like in chapter 2. We will also look at some model convergence diagnostics to check whether our model actually is behaving as we would want it to behave, those issues I will discuss later on. Finally, we will summarize the posterior distribution, right? Having figured out the marginal posteriors for mu and sigma, we will summarize it in a way that we can report it in a paper, for example, to tell the reader what we have learned from the data that we analyzed. So the example I'm going to work with is a very simple one. This is real data, but it was data generated by Bruno Nissenbaum, the first author of the textbook that we are using here. And basically what he did was he just sat down in front of the computer and started recording his button tapping times as he's pressing the space bar repeatedly. So you can use software to record the button tapping times there. So we are just modeling the button tapping times from one participant's behavior. Right? So to get access to the data that Bruno collected, we first install this library bcogSci. So this library is not available on the CRAN, the CRAN network where the libraries are available for R. You'll have to go to this website and follow the instructions for installing this package in R. So once you've installed the package, you can call it just like a regular package in our library bcogSci. This package contains a lot of data sets that are used in the textbook, and one of them is this space bar data set. Okay. So what does this data look like? So what this has is one column called T, which represents tapping times, button tapping times in milliseconds. Okay. And what you're seeing here is these numbers 1, 2, 3, 4, 5. They represent the trial IDs. Okay, so we'll use those later on. First of all, let's just look at this column of button tapping times visually and do a graphical summary of the data. What you'll observe is that the data is slightly skewed. So let me show you here. On the x-axis, I have button tapping times in milliseconds. And what you see is that there's a slight skew here to the right. And that is not surprising. So in reading time and button tapping times, you will see a skew in one direction because the data can only increase in one direction. You can't get less than 0 milliseconds button pressing times. So that skew we will model later on, but right now we'll ignore that problem and just pretend that these data are coming from a normal distribution. Obviously, that's an assumption that is patently false. But let's just assume that for now, just to get started, okay? All right, so the next step will be to define a likelihood function. Well, we already did that. We are going to assume a normal likelihood. So that's my normal likelihood here, okay? So I have two parameters. So I'm going to have to define some priors on these parameters. As I said, one could rewrite this statement as a linear model. These two statements here are exactly the same thing. They're saying exactly the same thing. Yeah. All right, so let's define some priors on the parameters. Just to get started, we're going to define a normal prior on mu with mean 0 and standard deviation 2000. This is not a very reasonable prior, but let's just start with that just as an illustration. And for sigma, we're going to define a normal prior with mean 0 and standard deviation 500, but we will truncate that normal distribution to the right such that all the values are greater than or equal to 0, right? So this is what those priors look like. This is the prior on mu. Here's the truncated normal prior on sigma, okay? All right. So the very first thing that we can do with this model, the model is the likelihood function and the priors defined on the parameters in the likelihood function. So one thing we can now do is we can derive what's called a prior predictive distribution. So what this does is we've got the likelihood, and remember with the normal likelihood, the R norm function generates random data for us. Now all we have to do is take a sample from the prior on mean, take a sample from the prior on sigma, plug it into the R norm function and generate as many data points as we want to. Then do that procedure again. with a new sample of mu and sigma from the prior. And so you repeatedly keep taking samples from mu and sigma's priors and plug them into the R norm function and generate simulated data. That becomes our prior predictive data. Mathematically, you can write down the prior predictive distribution like this. So this equation you will see in textbooks, but what I just described is all that it's doing, right? So you don't need to understand it mathematically, you can understand it intuitively. So what we're going to do is first take a sample from each of the priors, generate the number of data points you want to generate using those samples, and keep doing that over and over again. So that's what this code here does, right? I won't walk you through this code, but what I want to show you is some example data points that I produced, right? Having sampled from the mu and sigma priors. And what you'll notice is that this kind of data that my model is producing is not at all reasonable. Why is it not reasonable? It's not reasonable because it's producing negative button pressing times. How do you get a negative button pressing time? Not possible, right? So obviously there's something wrong with this model, right? And the prior predictive data is already showing us that there is some problem that we need to deal with, right? And we will deal with it later on. So these are some more simulated data sets that I produced, and you can see that occasionally the data, are in the positive range, but these button pressing times are pretty slow, right? 2.5 to 4 seconds. I mean, those are really slow button pressing times if you're just tapping the button quickly, So that's not a good representation of the underlying phenomenon that we're studying, namely button pressing. And here again we have, am I imagining this, or is this all negative reading times? Right, so this this distribution is producing just completely ridiculous data, right? All negatives. So nevertheless, the important thing that I'm showing you here is how you can generate prior predicted data having specified a likelihood and a prior distribution on the parameters. Having defined prior distributions on the parameters, right? Okay, so you could now, do something like this. You could also truncate the prior on the mu parameter, right? Such that not only is the sigma parameter truncated at 0, you could set it so that the mu parameter is also truncated. The prior on the mu parameter is also truncated such that it cannot have values less than 0. So that's what I've done here. I've truncated the normal, right? So I'm just taking samples from a truncated normal, which is truncated at 0 here, right? To produce truncated normal priors for mu as well. And then I generated, prior predictive data, and I still see negative data points. In this particular example, I don't actually see them, but if you were to generate, data repeatedly, you would see negative data points occasionally. And the reason for that would be is that even though the prior on mu is truncated at 0, so it can only have positive values, you may have a value for mu that is close to 0, and then in the likelihood function, which allows negative values as well, then you could end up with data that is in the negative range. So even though in this particular simulated data I just got lucky and I seem to have only positive values, it can happen that you would still get negative values here. We will fix all this later on, but I just want to demonstrate how you can use prior predictive distributions to understand how your model behaves and what kind of data the model generates, even before you have seen any real data. I'm going to show you now how you can generate prior predictive distributions using STAN, the probabilistic programming language that we are going to use in this textbook. So what we are first going to do is write out a STAN model in a character form, so as a text file essentially, and then we're going to feed that into some built-in functions in the RSTAN package to produce the samples from the posterior distributions. So let's take a look at some Stan syntax here before we get going with the modeling. So a Stan model is going to consist of several blocks: the data block, parameters block, and the model block. And sometimes you will also see this block, which I'm using here, the generated quantities block. Each of these blocks is demarcated by a curly brace. So for example, you see this curly brace here. And so in the data block, what I'm doing is I'm specifying the data that will go into this model. And because we are using the Stan model to just generate prior predictive distributions, the only information that goes into the model as data is the number of data points that we are going to produce. So that's the capital N. Int means that the capital N is of type integer. And notice that every command in the Stan model code is followed by a semicolon. That's because underlyingly this code will be translated into C++, and there's a convention to end each line with C++. So what we are doing is we are specifying a data type for this data object capital N, which is the number of data points, in the parameters block, which is also demarcated by curly braces. We are specifying two parameters, mu and sigma, which are of type real. So you always have to specify the type of the variable that you're defining. And here in the angled brackets, you see this text lower equal to 0 for both of the parameters. What we are doing here is stipulating that the mu and sigma parameters are bounded at 0. They cannot have values less than 0, right? So that's just a stipulation that is put here, a constraint that is put here on the parameters. Then comes the model block. And the model block, because we are only generating prior predictive data right now, we have not seen any data. We are just using the model to produce prior predictive data. So in the model block, there's only two pieces of information: the prior for mu and the prior for sigma. That's it. Okay. And so here in the generated quantities block, what we are doing is we're going to generate simulated data sets. So this is the y underscore sim. This will be a vector of length n. Okay. So we're going to be generating simulated simulated data. That means prior predictive data, and we'll be doing it as follows. We'll be producing n data points and storing them in the y-sim vector, which is of length n, by using the Stan equivalent of the rnorm function. So this normal underscore RNG stands for random number generator. So this is just the rnorm function in Stan, the rnorm equivalent in Stan. And so what this is doing is that it's generating random data given some prior distributions on mu and sigma. So notice that this is exactly what I did earlier in pure R. I took samples from mu and sigma, plugged them into rnorm, so this is normal RNG, and generated n data points each time. So that's what this code is also doing. So what I want you to appreciate is the tight connection between the R code that I wrote earlier to generate prior predictive data and the Stan code that I'm using here in the generated quantities block to produce simulated data, right? So how we would use this model is that we would first load the RStan library. Of course, you have to install the package first. And then what I've done here is that I'm just telling the session in which this R code is running, the number of cores that I have on my laptop so that it can do some efficient calculations. I've also loaded the BRMS library, which we are also going to use in a few minutes. So in any case, we are still working with the Stan code that I just specified. And so what I'll first do is I'm going to create a data object. In Stan, we expect the data to come in list type, not as a data frame, as in, you know, in LME4, in Elmer and linear models and all the standard R packages for data analysis. Data is always in a data frame format. In Stan, it's in list format. So I'm creating a list object here with only one piece of information in it, that is n equal to 100. So I'll be generating sets of 100 data points here. Okay. So here's my data. That's the list object, dat. And so what I've done here is in the stand code, the stand function, which is part of the which is a function provided by the rstand package, I give it as input the stand model that I had specified earlier. So if you remember here, in this character form, I had written and saved the stand model as a character type here, okay, prior pred. So I'm giving the stand function in the model code parameter here inside the stand function. I'm giving it the model as in character form. Here's the data, dat, and here I'm specifying the numbers of chains and warm-up and iterations that I need to run the model. So these are just default values inside stand, but I specified them anyway. So basically what I'm doing here is I'm asking stand to produce samples from each of the posteriors for the two parameters in the model, the mu and sigma, to produce 4,000 samples, a total of 4,000 samples. That means there are 4 independent sequences of samples that will be generated. These are called chains. And for each of those 4 chains, if I have 2,000 samples for, let's say, the parameter mu, and there are 4 chains, so then I have 8,000 samples. The first 1,000 samples of each of the 2,000 samples will be removed because those are initial samples that the sampler is looking at, and they may not actually reflect the posterior distribution. If none of this makes any sense to you, what you need to do is to go back to the YouTube lecture that I pointed to earlier, in which I talk about sampling. So that was at the end of chapter 2, the lecture for chapter 2. I gave you a link to the sampling lecture. It's also on the website for these lectures. So you can listen to the lecture and you will understand what warm-up is referring to here. We are just throwing away some initial samples because they may not be coming from the posterior distribution that we want. So what we have is 4 independent chains, okay, that are getting samples for the parameter mu, for example, 2,000 samples each in each chain, but the first 1,000 are thrown away as warm-up. And the total number of iterations, as I said, was 2,000. Therefore, in each chain, I have 1,000 samples, right? So if I have 4 chains, I have a total of 4,000 samples for each of the parameters in the model. So that's what the end result of this calculation will be. If I run this code, if I run this function, it will return an object containing 4,000 samples for mu and 4,000 for sigma, okay? So we can now extract the parameters and take a look at what the model tells us. In this particular case, what I'm actually interested in is extracting the simulated data points, the y_sim, right? What I'm interested in getting out of this model is these generated quantities, the prior predictive distributions. So that's what I've done here. So if you look here, this extract function is taking the model as input and pulling out the y_sim prior predictive distributions. Okay. So if you look at the structure of the y_sim, you will see that it contains 1,000 rows and 100 columns. So what this means is that, sorry, I misread this. It contains 4,000 rows and 100 columns. So it's a 4,000 by 100 matrix. That's what that ysim object is. So what that means is that the ysim object has 1 to 100 elements along each row, and there are 4,000 rows, right? And the reason why the ysim object has this structure, the reason that the ysim object has the structure is that This first row is the result of taking one sample from mu and sigma, from the prior distributions of mu and sigma, generating 100 data points. The second row is the result of taking another sample from the priors of mu and sigma, generating 100 data points, and so on all the way up to 4,000. Why 4,000? Because I have four chains, each of which delivers 1,000 samples. Right, so a total of 4,000 samples is what I have for each of the parameters for mu and sigma. So that's what that YSIM function is doing. YSIM object is giving me. It's giving me the prior predictive distributions. So I've got 4,000 instances of simulated data sets here. So I'm just going to extract the 100th data set that was generated. So I've just extracted one of these 4,000 rows, and I'm plotting the distribution of it, and this is what it looks like. Right? So this is an example that's being generated by this model that I'm assuming here. Notice one interesting thing about the prior predictive data is that it looks mostly reasonable, you know, as button pressing time a bit on the slow side, so 2.5 seconds, 3 seconds, but it looks roughly normal. The only abnormal thing is that it contains some negative reading times. Okay, so this model is not a great model of button pressing times, but it's good enough for our purposes right now. So I'm going to go with this model for now and see where it takes us. Okay, so now that we have taken a look at the prior predictive distributions, we generated them by hand, so to speak, using R, and we generated prior predictive distributions using Stan, the programming language. We are now going to fit the model in Stan using some data that we might have. Okay, so the button pressing data, for example. The purpose of looking at the prior predictive distribution, you know, in this section, I showed you how to generate prior predictive distributions. The point of this process of looking at the prior predictive distributions is to understand what predictions the model makes when given the model specification that you have, including the priors. Right? So it's a way to decide whether the priors and the likelihood that you have chosen are appropriate for the problem that you're studying. The answer in this particular case is clearly no, because of the negative reading times. There's something wrong in the model specification, that the model is producing negative reading times or button pressing times, right? So we will fix that later, but the point is that the prior predictive distributions are very useful to look at in order to understand the behavior of your model and the predictions made by your model even before you've seen any data. But now let's see what happens when we work with actual data to fit the model, right? So now we are going to modify the Stan code that I wrote earlier. Remember, the Stan code that I wrote earlier was only for generating prior predicted data. And that's why, if you look at the Stan code, what you'll see is that in the model block, I don't have any likelihood specification. I only specify the priors on mu and sigma. I only use the likelihood specification when generating simulated data using the normal RNG function here. Okay. Now, I'm going to now extend the Stan model to actually fit data that we might have observed. And so in order to work with real data, what we have to do is we are going to actually modify the data block to include not only the information about the number of rows of data that we have, but we are also going to specify a vector that represents the observed data that we have. Okay, so this could be real data, it could be simulated data, but what it's called is this variable y. It has length n and it's of type real. Okay, so this could be positive or negative numbers, but they will be of length n. Okay, it's a vector of length n. So we've added this one line to the Stan model to express the fact that we are now going to model the model some data as well. Okay. Then we come to the parameters block, which remains unchanged. We specified the parameters and constrained it so that constrained the parameters so that their lower bound is 0. The model block you're familiar with already. We have the prior specifications, but here's something new. The observed data y is now assumed to be coming from a normal distribution with mean mu and standard deviation sigma. Okay, so that's a new line in the Stan code that will be needed to actually fit the model and to produce posterior distributions for mu and sigma. Okay. In the generated quantities block, what do we have? We have the YSIM object and then the same code that we had earlier. This is for now. What will happen is that once we fit the model and have the posterior distributions for mu and sigma, once we have posteriors for mu and sigma, what this generated quantities block will do is that it's going to use not the prior samples from sigma, but the posterior samples from mu and sigma. It's going to use the posterior samples for the two parameters and plug them into the normal R and G function to produce simulated data after we have established what the posteriors are for the mu and sigma parameters, right? So in other words, the same function in the generated quantities block that was used to produce prior predictive data is now being used to produce posterior predictive data. That means future data after having seen the current data that we encountered in our experiment, right? And that all this happened simply because I added in the model block this one statement which asserts that I'm modeling the observed data as coming from a normal distribution with parameters mu and sigma. So the effect of adding this line here in the Stan code will be to generate posterior samples for mu and sigma, which will go into this code here in the generated quantities block, and the YSIM data that will be generated now from the generated quantities block will actually represent what's called posterior predictive data, the data that is generated by the model after it has seen the data that you collected. Okay, so this is in distinction to the prior predictive data that or distributions that we had seen earlier. So let's test out this model with some simulated data first. So we don't actually have to use the raw data that we have from the button pressing task. Let's start with some simulated data, and the advantage of doing that is that we will know exactly what the true values of mu and the true values of sigma will be because we'll specify them. So let me do that. So let me decide that I'm going to have 500 data points collected, so simulated data points. I've set a seed here. What this does is that it ensures that the random data that I generate each time will always be the same, no matter how many times I run this code. Okay? So I've got the true mu specified at 400 and the true sigma specified at 125. So these are my gold standard values. These are my known parameter values. Okay, that I'm going to use to generate some simulated data using R norm. So I'm generating how many data points? 500 data points, right? Because n is 500 with this true mu and true sigma. So that's my generated data, and then all I did here was that I just rounded the data so that the decimal points are gone, just for ease of viewing. And then I created a sim underscore data frame object, and this is just because I'm going to need it later on for working in case I want to fit the same model in LM or something. I would need that sim underscore data for entering into the LM function in the frequentist framework, right? So anyway, now I'm taking that data frame object sim underscore data and creating a list object called dat, which contains only one element here. Well, it contains two elements, sorry. It contains the vector of data and the length of the data frame of the vector of data, right? So n will be 500 and y will be all the data that I just generated. Okay, so let's fit the model again. This time we're going to fit the model using Stan. using Stan, we are going to use the second model specification that I just wrote, this model here, okay, which I just specified earlier, right? This model here is called M1, right? So what I'm going to do is I'm going to use that model in the Stan code, and I'm going to give it the data, the simulated data that I just created. Again, 4 chains and iterations 2000, etc. So these are all default numbers actually in Stan. So even if I had not specified all this part, it would have been enough to just write this much and have Stan run. Okay. So the result of running this function will be an object that contains posterior samples from mu and sigma. Okay, so that's what I'm going to get when I'm fitting the model to actual data. Earlier, I used the Stan function with a different model which only generated prior predicted data. So what that model was producing for me was the prior predictive distributions of the data. That model cannot produce posterior samples for me. So I might have misspoken earlier and said that that model produces posterior samples. Let me go back. Right, so talking about this original model that I had fit, I have a vague memory that maybe I accidentally said something like this when we fit this Stan function, right? This object that we get, I might have accidentally said that this contains the posterior distributions of mu and sigma. That's not correct, because there is no posterior distribution in this model, because it's only generating prior predicted data. That's the only purpose of the code that's written up in this prior pred model that I wrote earlier, right? So by contrast, in the second model, I'm generating posterior predictive distributions of mu and sigma, and so now when I run this Stan model, this object contains posterior samples of mu and sigma. Okay, so we can now extract those and look at those. So here's what I've done. I've extracted the samples for mu and sigma from the model, and you can see the posterior distribution of mu. This is the result of 4,000 samples, the distribution containing 4,000 samples. Similarly for sigma, I have that too here. Okay, so I can eyeball these distributions now and check whether they are reasonable or not, right? Given the priors and given the likelihood that I have. So if I look at this, the posteriors for mu and sigma, they seem pretty reasonable, because if you remember, the true value that I had set for mu was 400. That's that vertical line here. And the true value for sigma was 125. So what you're seeing is that the posterior distributions of mu and sigma actually contain the gold standard true values for mu and sigma. That's an indication that the model is reasonable. It's able to recover the parameters for the model that we have specified, right? So it's a test to see if the model behaves correctly if we give it data whose true values, underlying parameter values, are known to us. Okay? That's the advantage of doing this kind of modeling. So what I had shown you earlier is that we can extract from the Stan model the posterior distributions for mu and sigma, and this is a very useful way to establish whether the model behaves as expected, right? So what we did was we generated some simulated data with known parameter values, known point values, and then we checked whether the posterior distributions contain the true known values, the gold standard values. Another way that you can use to check the behavior of your model to see if it produces reasonable data is that after you have fit the model, you can produce some future data to see if that future data looks similar to the data that you had observed. So these are called posterior predictive checks, and formally the equation amounts to saying that you want to look at the distribution of future data given the data that you have observed. So you will see this equation in textbooks, but what it really amounts to is the fact that you have fit the model, you've got the posteriors on mu and sigma, and you're going to use those posterior samples for mu and sigma to generate new data, for example, in the generated quantities block of the STAN model specification. So that's all we are doing here. Okay? So the end result will be very similar. The end result of posterior predictive distribution generation will be very similar to that of the prior predictive distribution generation. So we'll have a 4000 by 100 matrix, right, containing future data that we can examine to see if it makes sense or not. In the textbook, there are good examples of this in more detail, so you should take a look at that. But what I want to talk about next is how you would implement this kind of a model in BRMS. So we implemented it in STAN. I wanted to give you a flavor for what the STAN code looks like. So that's why I introduced that simple example. But in most of the coding that we'll be doing from this point on, we'll be working, at least until chapter 5, we'll be working with BRMS, which is a convenient front end to STAN. So in BRMS, there's a function, there's a library called BRMS, a package called BRMS, and it's got a function called BRM, which has a linear model Elmer style syntax for fitting linear models and hierarchical models. So it's a very convenient syntax for people who are familiar with the LM function in R or the Elmer function in R. Okay, so in the BRMS function, we could specify the same type of model that I had discussed earlier by first specifying a vector of priors using the set underscore prior command, which specifies the priors for each of the parameters in the model. So the intercept here refers to the mu parameter because we're talking about linear models here, and that's the intercept in the linear model, and sigma is the residual term here. Okay, so we are defining priors for mu and sigma, and notice though that for sigma we don't say anywhere that we are truncating the prior. That's understood in BRMS because sigma can only be positive. Standard deviations can't be negative, right? So what BRMS does internally is that when you say normal 0, 500 as a prior for, when you specify a normal 0, 500 prior for sigma, it truncates it at 0 automatically, okay? It doesn't do that for the intercept parameter. So this is an untruncated prior, and this is a truncated prior, and you can't control that in BRMS. It's done for you when you are trying to specify the prior, when you specify the prior for the sigma parameter. Okay, so we've created this object containing the priors, and so now the BRM syntax is as follows. It's just like the LM syntax in R. Got the dependent variable, here's button tapping times, and this is the intercept. So the button, we are now actually looking at the real data, no longer simulated data. So in the button time, for the button tapping times, we have an intercept which represents the mu, the average button tapping time. Here's the data set that I had loaded long ago, right? Here are the prior specifications, and these are the iterations and warm-up and chains that I mentioned earlier. And here there's something new. I'm specifying the likelihood function as the Gaussian, right? So we are assuming a normal likelihood. Gaussian is just another way to talk about the normal distribution, the normal likelihood. There's one more control parameter that I've put here that is discussed in the textbook in more detail, but this control parameter only serves to modulate the behavior of the sampler, the Hamiltonian Monte Carlo sampler. Those details I'm going to elide here for now. Okay, so once I fit that model, we can extract the posteriors again, just like I showed you earlier for STAN. You can extract the posterior samples, and the code for that is of course available in the textbook and also with these lecture notes. You can look at that later. But here's the mu posterior for the mu and the posterior for sigma. Okay, very similar to the simulated data that we had generated, but obviously slightly different because now we are working with real data here. Another way that you can look at the model behavior is by looking at so-called trace plots. And what these trace plots are showing you is the 1000 iterations in each of the 4 chains. So there are 4 chains for mu here that are being displayed. So there are with 1000 iterations each, and you can see that all these 4 chains are sitting on top of each other. That means each of the 4 independent chains are sampling from the same distribution. Similarly, you see the same type of pattern in the sigma for the sigma parameter. 4 chains sitting on top of each other, total of 1000 iterations each, and the sum of those 1000 times 4 iterations is of course 4000 iterations. So that's how we end up with 4000 samples by default, unless you change that specification in BRM or in the stand code. So this kind of plot is called a trace plot, and it's intended to show that the chains are mixing. That's the phrase that is used, and what that means is that the chains are all taking samples from the same distribution. If they were not taking samples from the same distribution, they would be not mixing, they would be spread away from each other, right? So what they say in the Bayesian terminology is that the trace plots should look like fat hairy caterpillars, right? You can see the metaphor there. So if these chains look like they're mixing nicely, you will see this kind of shape, and later on in the textbook you will see examples of chains not mixing, and you will see examples of what you can do to fix that kind of problem. You can also summarize the posteriors alongside the trace plots, right? So there's code for that available as well, so you can check what the underlying code is to produce these kinds of plots. But typically when you're publishing a paper or reporting the results of an analysis, it is not normal to display the trace plots, right? So generally these trace plots are only for you to understand the behavior of the model while you're doing your analysis. When you report the results of the analysis, you just report these kinds of histograms or some other kind of density plot or something to show what the posteriors for the parameters look like. Okay, so the last point regarding the posterior distributions of the parameters is that we want to, when we write a paper, we want to summarize the posteriors in a way that the reader can understand what happened in the model and what the result of the modeling was. One way to summarize the posterior is of course graphically, and one generally does that. Generally, when you're reporting the results of a model fit, you will illustrate or present the posteriors as a figure for sure, but you can also present model, summary statistics that allow the reader to get some idea of what the basic range and mean and so on of the model is, of the parameters is, right? Okay. So how do we do that? So let's just go from beginning to end to get an idea of how we would report such an analysis. I specify my priors, I fit the model, okay, just like I did earlier. And now we compute the posterior probability of a particular parameter, for example, the mu parameter being larger than 170. I could do that by extracting the samples. That's what I'm doing here, right? I'm extracting the posterior samples from the fitted model, right? And then once I've got the vector of samples, so these are 4000 samples for the posterior of mu, I can now use the mean function to figure out the proportion of cases where the samples are larger than 170. Okay, so the proportion of cases where the samples are larger than 170 milliseconds is 14 point something percent. Okay, that could be a plausible summary to answer a scientific question that you might have about button pressing times in this case. Another way to summarize the results of your computations would be to just compute a 95% credible interval for the parameter of interest, right? So if your posterior distribution for the mu parameter looks like this, right, what you can figure out is the lower bound and upper bound of this interval such that the area under the curve between the lower and upper bound, here's the lower bound, here's the upper bound, is 95%. 95% is an arbitrary choice. You could have chosen 73%, you could have chosen 81.25%, it doesn't really matter. Of course, I'm just being facetious here, but the convention in linguistics and psychology is to report 95% credible intervals. That comes from the 95% frequentist confidence intervals idea. And so this is a very useful interval to report as a summary statistic, because what it tells you is the range over which you can be 95% sure that the value of the parameter lies, given the statistical model that you assumed and given the data that you observed. It's not necessarily the true values of the parameters, it's just what you have learned from the data given the model, which includes the prior for mu and the data that you have observed. Okay? So this is called a 95% credible interval, which I generally abbreviate as C_RI, right? So credible interval, to distinguish it from the frequentist confidence interval, right? So the frequentist confidence interval is very different in meaning than this interval. So the credible interval is actually telling you the range over which you can be 95% sure that the parameter mu lies, given the data and the model that you have, right? So the frequentist confidence interval, this confidence interval in the frequentist paradigm is something different, right? What it says is that if counterfactually you were to run the experiment over and over again, okay? So let's do it like this, right? So let's say I run the experiment 1 time, 2 times, 3 times, let's say 100 times, okay? If I run the experiment over and over again, oh, cannot actually see this. Here you can, it's okay, right? So you run the experiment over and over again, and let's say the true value of the parameter is this line here, okay? So that's the true value of the mu parameter, okay? The frequentist confidence interval means that if you were to counterfactually run the experiment over and over again, 95 of the 100 confidence intervals that you would compute each time, 95% of the confidence intervals would contain the true mu value, that is this horizontal line. So you, in 95% of the cases, you would end up with something like this, something like this. But in 5% of the cases, there would be in 5% of the cases, you would have a situation like this, that the true mu, this horizontal line, is not contained in the confidence interval. So that's the meaning of the frequentist confidence interval, right? Which is very different from the meaning of the credible interval. Well, the thing is that the credible interval is actually a much more intuitive quantity. It tells you something that you really want to know, right? With the frequentist confidence interval, when you compute one frequentist confidence interval in your frequentist analysis, you have one of these 100 confidence intervals, but you don't know which one it is. Is it this one or is it this one? Right? You have no idea, right? So the probability statement in the confidence intervals refers to this hypothetical repeated sampling of data that you never even collected. And often you will find in the frequentist world that people will interpret the frequentist confidence interval to mean what we actually mean when we talk about the credible interval. But that's not possible. It's not possible to talk about frequentist confidence intervals as a Bayesian credible interval, because the mu parameter in the frequentist confidence interval is not a random variable. It doesn't have any probability distribution. Therefore, you cannot make a probability statement about the mu parameter that it lies between this lower bound and this upper bound. You can make that statement here in the Bayesian framework. You can say that this probability is 95%, right? You can say that we've fallen off the edge here, so let me just write it here, is equal to 0.95, right? So we can say that here in the Bayesian framework we can make this kind of statement. Why? Because mu is a random variable. In the frequentist framework, mu is a fixed point value. It doesn't have any probability density function associated with it. It's not a random variable. So you cannot make such a statement about a point value. So that's a very important difference between the frequentist confidence interval and the Bayesian credible interval. So the credible interval is a very useful summary statistic that you can use to report the results of your analysis. You can extract the credible interval from the result of a fitted model, right? Here's the fitted model here. And so we can extract for the intercept which represents the mu parameter, you can extract the 95% credible interval. And another way that you can do this is by obtaining the posterior for the mu parameter. So if you remember earlier, I had extracted the posterior samples for the mu parameter and then just run it through the quantile function in R for a particular lower and upper bound. So here I'm computing just some arbitrary credible interval, a 73% credible interval, but you could do that for 95% credible interval too by putting in 0.025 here and 0.975 here, right? So you can choose which interval you want by deciding on the lower and upper quantiles. The important thing to notice is that a 95% credible interval is defined so that it has equal probability mass in the tails. So that's why we choose values like these for 73%, right? So basically what we want is the total probability underneath the curve for a 73% interval, right, will be 1, right? So if I want a 73% interval, then what I want to have in the tails is 1 minus 0.73 in both the tails, right? So let me just draw this. So here's my distribution. I want to figure out a 73% credible interval. I want to make sure that the area under the curve here is 0.73. Therefore, the tail area has to sum up to 1 minus 0.73. And so because I want equal tailed intervals, right, same probability mass in both ends, I'm going to divide this by 2, and that's the amount of probability mass I want in each of these tails, right? So that's how I end up with 0.135 and 0.865 to define this lower bound and this upper bound. The next thing I want to talk about is the prior specification and how that could impact the posterior distributions once you have seen the data, right? So I already discussed in chapter 2 how the posterior or posteriors in a model depend on the informativity of the prior and the amount of data that you have. So you can actually understand the effect of the priors by varying the priors to be less or more informative to see how that changes the posterior distribution, right? So that's called a sensitivity analysis, and we will talk a lot more about this later on when we look at concrete examples of real life data, okay? So let's just take these kinds of uniform priors. So earlier I'd been using normal priors, if you remember, right? So now I'm just changing the priors to uniform priors for mu and sigma, and I could refit the model with these new priors. Okay, so that's what I'm doing here. And for the uniform, where I've got a lower bound of 0, when I'm looking at the parameter sigma, I'm defining a uniform 0, 500 prior for sigma. This lower bound For technical reasons that have to do with BRMS syntax, we need to explicitly specify the lower bound and upper bound as well. It seems very counterintuitive, but it has to be done. The same thing happens here because again, for the intercept, for the mu parameter, again I have a 0 to 5000 bounded prior. So I have to specify these lower and upper bounds, and the reason for that is in the BRMS syntax I have to do this, not in Stan. But the reason for this is that the sampler then will never look outside that range when it's trying to obtain samples from the posterior. So this is just a way to constrain the sample space, the sampler's search space when deriving the posteriors. At least that's what I think this is all about. Okay? Anyway, so that's just a minor technical detail here, but the important thing is that again I'm going to fit the same model. I've got my dependent variable button pressing, button tapping times, intercept. I've just got an intercept which represents the mu, if you remember the beginning of the lecture, and everything else is familiar to you. I've got my new prior specification here, and everything else is more or less the same as before. And now we can look at the results. So what we get as an output, so this is a special function that we wrote. It's hidden in this lecture notes file. So when you look at the R Markdown file, you'll find it at the very top of the R Markdown file, this short summary function. It just strips out some of the redundant information and gives me the critical information that I need to display here. And so what I'm looking at as an output of this model is the summary statistics on the intercept, that is the mu parameter, and the summary statistics on the sigma, that is the residual standard deviation. So what I get is an estimate of the posterior mean and the 95% credible interval. You see that over there? Similarly, I get an estimate of the posterior mean for sigma and a 95% credible interval. So if I were writing a paper about button pressing times or button tapping times, I would report these summary statistics, the means and the 95% credible intervals in the paper for the reader to help them interpret what we learned from the model and the data. Okay? Now, I'm going to talk a lot more about this later on, but one thing we want to do when we specify a model is that we do not want to specify too informative a prior. Because if the prior or priors are too informative, then the data will have almost no influence on the posteriors. So the posteriors will look exactly like the priors, right? You learn nothing from the data if you specify too tight a prior, right? Similarly, if you specify at the other extreme, if you specify too vague a prior, then the posteriors will look very similar to the maximum likelihood estimate. Right, so if you were to fit a frequentist model and compare the estimate of the mean for the intercept and the 95% confidence interval, not the credible interval, the confidence interval from a frequentist model with the 95% credible interval of a Bayesian model with very vague priors, what you would find is that they are very, very similar, if not identical. Okay, they're going to be very close to each other. So the choice of prior is important. We don't want to have too informative a prior, unless of course you have really good reasons for it, as we will see later on. And we don't want to have completely uninformative priors either. Right? We want to have priors that are reasonable and make sense in the context of the problem that we are studying. This sounds very mysterious, I know this, but you will see that there is a very clear logic to the process of deciding on what the priors should be in a particular model. So you will understand this and you will gain experience with this as we look at more and more examples. Let's now look at a second example of a linear model in which we add one more term in the model to expand the complexity of the underlying process that's producing the data. So remember, what we're talking about is button pressing times, and until now we've been assuming that the data were being generated from a normal distribution with some unknown mean, right? So we have button pressing times t, and these are coming from a normal distribution with some mean and some sigma, and the model was defined so that there were some priors defined for mu and sigma, right? So we had some priors. For example, in the last example I showed you some uniform prior. I don't remember the exact numbers, but let's say this one, and could have another uniform prior like 200. Maybe my numbers are off from the example I gave earlier, but this is an example of a model. This is my model, this is the model, and we are assuming that the data are coming from this generative process, right? So we can extend this generative process now by assuming that the data, why can I write this? Here's good, right? So by assuming that the data are actually coming not just from normal distribution um, with mean mu, but that there is also another parameter which is a function of the trial ID. Okay, so the trial ID in the data that determines the button pressing time. So what this part would express now is that as the experiment proceeds, as you keep going through the experiment, you might actually become habituated to doing the experiment, and so you might speed up, or you might get impatient and speed up. Alternatively, you might get tired and start slowing down, right? So that impact of the trial on the button pressing times can be expressed by adding one more term in this equation. The way that we will model this situation by taking trial ID into account is as follows. We are first going to take the trial ID from the data frame. Remember, the df underscore spacebar data frame has two columns. One is the button pressing times, the button tapping times, and the other column represents the trial ID. So what we are doing here is that we are computing the centered trial ID. What that means is this trial vector, the vector representing the trials, from this vector we subtract the mean value of that vector, and what that does is it creates a centered vector such that the value 0 in the centered vector now represents the mean trial ID. Okay, so the trial IDs, once they are centered, will be either negative, 0, or positive. When they're negative, they represent trial IDs that are below the average trial ID, and the trial ID that is 0, or the ID that is 0 will represent the mean trial ID, and anything positive or higher than 0 will represent trial ID larger than the average trial ID. So that's what centering is doing here. Centering is a very useful step when you're doing linear modeling, and this will be discussed in detail later on when we talk about more complex linear models, but we will always be centering our predictors in our multiple regression models. So this is this is now what we call a multiple regression model, right? So there is an intercept here that represents the average button tapping time, and there's a new term here, centered trial, multiplied with a new parameter beta, which represents the impact of trial ID on the button tapping times. Okay, we have capital N data points, and so T underscore N represents the vector of N data points that we have, and what we are trying to do here is we are modeling the N data points as a function of trial ID. Okay, so now because we have three parameters, we are going to have to define priors not only for the intercept, which is called alpha here. So don't be confused by the terminology. Sometimes the intercept is called alpha, sometimes it's called beta 0, and this term here is called beta 1. Sometimes this is called beta 1 and this is called beta 2. Sometimes, and this is something I did in this lecture earlier, it's called mu. So don't be confused by that. It just represents the average button tapping time in this example. Whatever variable you want to call it is up to you. So alpha is the intercept now. We define some prior on that, and then another prior is defined on the beta parameter, which represents the effect of trial. Okay, and then there's the residual term that is a prior, which is a truncated normal. Okay. So one question that we will always ask whenever we are starting to work on a new problem is, when we define some priors for the parameters, do the priors make sense? How do you determine that? Prior predictive checks, right? That's an easy way to figure out if your model is producing reasonable data. Usually when you're working on a research problem, you know roughly what the data should look like, right? And if it's button tapping times, for example, you know that the data are bounded at 0. It can't be less than 0. And you know that a button tapping time of 5 seconds or 10 seconds or even 1 second seems implausible. That already gives you a very good ballpark idea of what a reasonable range of button pressing times is going to be. All right? So in any case, here are the priors. We're going to fit a BRM model, right? And so the prior specification I've already discussed for the intercept. There's nothing new here. Here we have something new, right? Here we are defining a prior for a new coefficient in the model, and that's the C underscore trial term. That's going to be a new column in our data frame, right? So BRMS, unlike pure STAN, will allow data frames of the classical R type to be given as input for fitting the model. And so the data frame containing one new column, the center trial ID, will be what's being referred to here when I say coefficient equal to C underscore trial, right? So class B represents the fact that I'm talking about the so-called fixed effects parameters, the intercept and slope parameters. In this case, I'm specifying which slope parameter I'm talking about in the linear model. Here, in the first specification for the intercept, I just have to say that the prior for the intercept is such and such, because the word intercept is a reserved term in BRMS, and so when you say intercept, it's clear that we're talking about the alpha term in this model here, right? This alpha term here. Okay, and then you have the third part, which is the prior for the sigma, which is all familiar. And so we fit the model. The only new thing in this model now is this specification, which you should be familiar with from your linear modeling class, by which you must have taken in the past. So we're just modeling the button tapping times as a function of an average button pressing time and the effect of centered trial. All right, so I'm skipping over all the prior predictive checks and all that stuff. So we can now extract the posterior distributions of the parameters, assuming that the model is reasonable, right? And so what we get as a posterior distribution for each of the parameters, here's the intercept parameter, here's the slope parameter, that means the effect of trial, and the residual standard deviation. So because we have three parameters, we have three posterior distributions. These are marginal posterior distributions, right? Underlyingly, the model is computing a joint trivariate distribution for all these three parameters. We are extracting the marginal posterior distributions from this multivariate distribution, just like I discussed in chapter 1. Okay, so the important question for us in this kind of model is usually, what is the effect of trial on button tapping times? Does the trial ID increase button tapping times, or does it make button tapping times get faster, right? So the question then is, graphically, the question is the following, right? What we want to know is, as time is going by, the trial ID represents time. So let's say 0 is the center point here, so centered trial ID, right? So what can happen as of to button tapping times as a function of trial ID is that you could have a trend like this. You could get speed ups as time goes by, or you could end up having some kind of slowdown or something, the participants are getting exhausted or something like that. Or you could even have a situation like this that nothing changes, they just steady at a steady pace, right? So these are possible ways, linear relationships that are possible. Of course, the relationship may not be linear, it could be non-linear. I'm just simplifying the story to talk about everything in terms of a linear trend. Okay? So these are possible things that can happen. And so what we really want to know, if you want to know which of these worlds is indicated by the data that we have, what we are really asking is, in the model, what we are asking is that the button tapping times, the alpha plus beta parameter here, which is representing the effect of trial, is this beta parameter positive or negative? If the parameter is positive, then what that means is that as trial ID increases, the button tapping times are going up. If the beta parameter is negative, that means as trial ID increases, the button tapping times are going down. If the beta parameter is 0, that means the effect of trial ID on button tapping times is non-existent, right? So that's what the interpretation would be of the beta parameters. More specifically, what the beta parameter does is it tells us what the expected increase in button tapping times is if you increase the trial ID from the mean, right? If the trial ID was the mean, it would be the value 0. So beta times 0 would be 0. The expected button pressing time when the trial ID is 0 is alpha, right? But what the beta parameter is telling you is that if you increase trial ID by 1 unit, that means if you go from 0 to 1 trial ID, then the expected button pressing time is alpha plus beta. That's what the meaning of this parameter is. Now if beta is positive, that means button pressing time is going up. If it's negative, that means button pressing time is going down. Of course, we are just assuming here that the relationship is linear. It need not be. Okay? So the key thing of interest for us is the beta parameter. We want to know what the posterior distribution of the beta looks like. We can extract the posterior samples from the fitted model for all the intercept and slope parameters in the model. That's the intercept and this slope parameter here. So what we get is a vector of 4,000 samples for the intercept, a vector of 4,000 samples for the slope. And now, because these are vectors of samples, we can just calculate some summary statistics on these. So just look at the beta samples, the effect of trial ID. I'm extracting the vector containing the posterior distribution of the beta parameter, given the model and data, calculating the mean, and calculating the 95% credible interval. You see that over here? I'm using the quantile function. I'm computing the 95% credible interval, and I could use that to summarize my posterior distribution and report in the paper. For example, let's say I'm writing a paper on the effect of button tapping, of trial ID on button tapping, and so we can summarize the statistics like this. The mean button pressing time is 168 and the 95% credible interval is this one here. We will ignore the standard error column. I wish it was not there because it can be very misleading because of the rounding errors. So let's just focus on the credible interval and the estimate. If we want to compute the standard error, that's never happened to me in my entire life. So I think we could do it, but we don't want to do it. Okay, so just forget about this. Let's talk about the 95% credible interval because that's a very informative range that tells us what's the range of plausible values given the model and the data for the average button tapping times. And similarly for the effect of trial, this is the range 0.07 to 0.11 milliseconds. Okay, so this is on the millisecond scale that we're getting. So what this model is telling me is that the average button tapping time is 168, and 1 unit increase in the trial ID is expected to lead to on average an increase of 0.09 milliseconds in button tapping time. That's what the prediction is here, okay? Or what the model tells me. Okay, so another interesting way to check model behavior. So we've already talked about this before, right? We do prior predictive checks before we've seen the data. After we've seen the data, we do posterior predictive checks. Another way to graphically summarize the posterior predictive checks is to overlay the observed data with the posterior predictive data. And that's easy to do with BRMS. So you don't need to do much coding for that. You fitted the model. Here's the fitted model in BRMS, right? And so I'm just using the built-in function called pp_check, which produces 100 samples from the posterior predictive distribution and overlays on top of it the observed data. So Y is the observed data. This is the actual button pressing data that we are working with. And Y rep, those blue lines there, those are the posterior predictive distributions. And you can see that they're pretty okay. I mean, they're overlapping. There's a slightly wider spread in the posterior predictive distributions that is not there in the actual data, but I would not overinterpret that. I would say it's a reasonable model. Okay. Now, having said that, right, one could actually improve on this model a little bit. As I mentioned at the very outset of this chapter, the lecture for this chapter, the button tapping time that we have is not really normally distributed. It's got a skew towards one side because 0 is a lower bound, a hard lower bound on one side. Can't have less than 0 milliseconds button tapping times, and so button tapping times can only increase in one direction. So because of this skew in the data, we are going to assume a different likelihood function to model the underlying process that produced this data. That underlying likelihood is the log normal. What I'm going to show you now is how the log normal likelihood arises and the basic assumptions here, right? So the log normal I'm going to write like this. So let's assume the data are coming from a log normal. So I will, just to save space, I'm going to write ln, although I meant to write log normal here. And so the log normal is similar to the normal distribution in the sense that mu and sigma are the parameters in the log normal distribution, but these parameters are now going to be so let's say the data are coming from the button tapping times. So these data are on the millisecond scale. Okay. In the log normal distribution, these parameters are going to be on the log scale, the log millisecond scale. Log millisecond scale, right? So this is important to understand because what you're going to get out of a log normal distribution, the kind of data that will be generated from a log normal distribution will not be on the log scale, right? So if the parameters are defined on the log millisecond scale, the data being produced is on the millisecond scale. And for that reason, if we were to have button tapping times or reading times or some positive only data like that that has a slight skew, you know, this kind of skew that I just showed you a few minutes ago, this kind of skew with 0 as a lower bound, then we could assume that those data are coming from a log normal distribution. And so an identical way to write this generative process, is to say log of y is coming from a normal distribution with the same mu and sigma parameters which are on the log scale. So the parameters, these parameters are the same parameters here, but this time they're coming from a normal distribution, and what has changed is that we have log transformed the dependent variable. So these two statements are completely identical. Okay, so there's more discussion about this in the textbook, but it's important to understand that if you're assuming that the underlying generative process for the data is log normal, then we could assume a normal likelihood, but then we have to log transform the data. And that amounts to assuming for the original data that the data are coming from a log normal distribution. Okay? So what I'm going to demonstrate to you now is how the log normal distribution works. So let's assume that the mu and sigma parameters are 6 and 0.5 respectively. What I'm going to do is I'm going to generate 100,000 data points from the log normal distribution. Right? So what happens here in this code is that this line here, which I'm going to highlight, this is the critical line. What this is doing is that it's using the RL norm function. So remember the R norm function that we used for generating normally distributed data? We are using the RL norm function here to produce 100,000 data points with mu equal to 6 and sigma equal to 0.5. So these parameters, as I just mentioned, are on the log scale, and these parameters are on, well, in the button tapping time example, they would then be on the millisecond scale. Okay, so this is just some code for plotting the figure after we've generated this data. So I'll just show you the result now. If you look at this figure here, this is the log normal distribution. It has the right properties. It has exactly the shape that we would expect in button tapping times or reading times and things like that. So positive only data. So given this kind of simulated data, it's a reasonable starting point to assume that we could use the log normal likelihood to as a generative process for modeling the data that we have. Now, what I wanted to also show you is that you could actually take data from a normal distribution and then with the mu and sigma parameters as 6 and 0.5, just as in this example, I could just generate data not from a log normal, but from a normal distribution and then exponentiate that distribution, right? The resulting output of that normal distribution. So I'll just show you the code for that. Let's just go up. So here, what I'm doing is that here, okay? So what I'm doing here is that I'm using the R norm function to generate data, 100,000 data points from a normal distribution with mu equal to 6 and sigma equal to 0.5, just like in the log normal earlier. And then what I'm doing is I'm exponentiating the resulting randomly generated data. And if I plot that exponentiated data, look, it has the same shape as the log normally distributed data. So these are two equivalent ways to talk about the log normal distribution. That's why I said earlier that if you take the log of, for example, reading times and assume a normal likelihood for those reading times, you are assuming that the original scale, the millisecond level data that you observed, is coming from a log normal distribution. Okay. All right, so what we can now do is we set up a new model. In this model, we are assuming a log normal likelihood for the button tapping times, and we're assuming an intercept and a slope parameter. So looking at the effect of centered trial on button tapping times, we have capital N data points here. And the priors is just like before, except what has changed now is that these parameters now are on the log scale. Therefore, the priors have to change as well. So earlier we had very broad priors because we were assuming that we are modeling the millisecond level data as coming from a normal distribution, right? So we could allow things like 2000 milliseconds or 8000 milliseconds. Now we're on the log scale for the parameters. Therefore, the priors on the parameters have to reflect that fact. So a normal distribution going from 0 to 10 is actually a very vague distribution because this is on the log scale, right? So if alpha represents the average reading time, okay, on the log scale, on the millisecond scale, a prior with 0, 10 as the parameters in the normal for the as the hyperparameters, that implies a very widely spread out a priori range for the average reading times. Okay, so do not be confused about the scale of the hyperparameters when you're working with the log normal distribution. It's a very common mistake that students make. They forget that they've switched to the log normal likelihood, but they continue using the priors from the normal likelihood that we had discussed earlier. So you have to be very careful about which likelihood you're assuming. Okay, so here we go. We define the priors. So these priors are spelled out here, and then we run the BRMS model, and then we can examine the the posteriors and figure out what the interpretation is of the parameters. Okay, so what you're looking at here um, in this output here, what you're seeing is the estimates of the intercept and slope parameters on the log scale. So the model here is effectively assuming that the button tapping times are coming from model where or let me not write it like this, let me just fix that. The button tapping times are coming from a log normal distribution, right, with an estimated intercept of 5 point something, so just say 5.1 here, okay, and a slope of 0.005, right? Is that what it is? Can't really see that well. 0, 5, and then centered trial, I'll just abbreviate that here. So as this is the entire mu in the log normal, and then there's a sigma parameter here, which actually I didn't print out, but there's some estimate for sigma there. That'll be the posterior. Okay, so let's not worry about that for the moment. So the interesting thing now is that we have these intercept and slope parameters now described or estimated on the log scale, right? We, however, have the data on the millisecond scale, and so we would want to ideally interpret these parameters on the millisecond scale. So really what you can do is, if you so as I said earlier, this kind of log normal likelihood amounts to assuming that you have log of the t coming from a normal distribution, right? Coming from a normal distribution with the same mu and sigma parameters as we have estimated here from the model. So the hats represent the estimates from the model here. Okay? Mu hat is the estimate from the fitted model, right? So now if we want to obtain the interpretation of the intercept and slope parameters on the millisecond scale, because as human beings it's hard for us to actually interpret what's happening on the millisecond scale. We want to be able to think about the problem on the original button tapping scale that we're working in, the millisecond scale. So remember that the intercept here represents the average button tapping time, right? And so what we can do, one convenient way to back transform the log scale estimate to the millisecond scale is to exponentiate the intercept. So if you take the exponent of the intercept estimate, we get the back transformed median value of the average button pressing time, right? So it's discussed in the textbook, we discuss this more in the textbook, why we use the median and not the mean, but you can take a look at that later on. But this is a very convenient way to actually back transform the estimates to back to the millisecond scale. So whatever the result of this calculation would be the under this model, under the log normal likelihood, would be the um, estimated average button tapping time. So what we want to also now do is to interpret the slope parameter. So now the thing is that because of the fact that we are working on the log scale here, the intercept is going to influence what the impact of the slope parameter is, right? This is also discussed in the textbook in detail, so make sure to read the chapter, right? But if I want to know what the impact is, so this represents the median tapping time, right? In milliseconds, right? And if I want to now know what the impact will be of 1 unit increase in the trial ID on button tapping time on the millisecond scale, I would compute it like this. I would take 5.1, the intercept, plus 1 unit increase means 0.0005 times 1, right? So um, this this term here, once I've added up these terms and exponentiated them, they will give me the change in the button pressing time, and obviously it will be a larger value than the button pressing time for the intercept, right? So the 1 unit change, the effect of the 1 unit change in the trial ID, right? So the reason we have to take the intercept into account here when computing the median 1 unit change here is that if the estimate for the intercept had been 6.1, for example, then there would be a much larger increase in button tapping time when 1 unit is increased from 0 to 1, right? So you can check that if you play with R a little bit, just change this to 6.1 and then look at what you get when you exponentiate this. So you can't actually ignore the intercept in these kinds of nonlinear functions, and that's why when we want to know what's the effect of increasing the trial ID by 1 unit, we're going to have to take the intercept into account. All right, so now that I have these two quantities, right, I can just take the difference between these two to find out what the increase in button tapping time is expected to be with 1 unit increase in trial ID. Now that I've explained how you can back transform the estimates on the log scale, assuming a log normal likelihood, these estimates here, back to the millisecond scale so that you can interpret the results of your analysis, I'm going to do that calculation now for you. So let's do this. So first of all, what I'm going to do is I'm going to extract the alpha samples, the samples of the intercept from the model, right? So that's I've extracted the vector of 4,000 samples for that represent the posterior distribution of the alpha parameter in the model. And similarly, I'll do the same thing for the beta samples, right? So I'm pulling out the slope parameter samples. So these are the posterior distribution samples for these two parameters. And now I'm going to start the back transformation, right? So how does that work? Let's take a look here, right? So what I'm doing here is that I'm subtracting two terms here. This term here is the exponent of the alpha samples. So what I'm doing is I'm exponentiating the 4,000 samples I have for the alpha parameter and subtracting that vector, that exponentiated vector, from this term here. So this term, the first term here, here, right? This first term is the alpha samples plus the beta samples exponentiated. So what this term is expressing is the back on the millisecond scale, it's back transforming the alpha and beta estimates such that it tells you what the button pressing time would be when you have a centered trial value of 1 compared to a case where the center trial value is 0. That's why the beta parameter is missing here. So the difference between these two exponentiated terms, gives me the effect of going from the average value of the trial ID to 1 unit higher. The effect on the button tapping times when you go from the average trial ID to 1 unit higher there, right? So once I have this vector, right, this vector is now back on the millisecond scale, right? This tells me the effect of going from trial ID 0, that is the mean, to 1 larger than 0, right? Then I can calculate some summary statistics, so that's what I did here, right? I calculated the mean of the back transformed value and the lower and upper bounds of the 95% credible intervals. So what I would report in the paper then would be the estimates representing, the effect of trial ID back on the millisecond scale, right? So that's what I've done here. So you can see this here. My estimate of the effect is 0.09 milliseconds. That's the credible interval here. And you could also compute quantities like these where if that's what is of interest, if you want to know what the probability is that that parameter is greater than 0. This is not a hypothesis test. This is just a way to quantify whether the probability mass is largely positive or not. Okay? So I'm going to talk about hypothesis testing later on, but this is just one possible way to summarize what you have learned from the model, having back transformed the estimates to the scale in which you can interpret the results for the research problem that you're working on. So one thing to notice here is that underlyingly R will produce 7, 8 decimal places. So you should not report 7 to 8 or 9 or 10 decimal places. Just use common sense to make the result easy to read and interpret. So if there are, for example, if the result had been 0.009, I would have used 3 decimal places, right? But not more than that, right? Okay, so that's the log normal distribution. You can now look at the posterior predictive distributions to check whether your fit has improved as a result of changing the likelihood function to something more reasonable, right? So this is what I've done here. So we are familiar with this kind of plot, so I don't need to spell it out too much. The black line is the observed data, and now you see that the posterior predictive distributions, which are the blue lines, they align quite a bit better, quite a lot more with the observed data. So just graphically, you can eyeball the posterior predictive distributions to see that your model is somewhat better now compared to the earlier model where we had assumed a normal likelihood. Okay, so this is basically just rewriting the model. The important thing to remember whenever you're using the log normal likelihood is two things. First of all, define the log normal likelihood as the family. Secondly, make sure that the parameters are on the log scale, right? Now, alternatively, what you could have done in this kind of model is, instead of modeling the button tapping times on the original scale, you could have just log transformed the button tapping times, okay? So you could log transform the button tapping times, and in that case, you would assume family binomial. This is what I was showing you earlier, that the two things are equivalent, okay? So then this time I would, in the BRMS model, I would assume a Gaussian likelihood, okay? And is this even visible? Sorry, maybe the pen is not really working properly. So this, I meant to write Gaussian here. right? So if you're going to log transform the data, you're going to use the Gaussian family likelihood, Gaussian likelihood. But remember that in this situation too, the priors are still going to be on the log scale, right? That's the demonstration I gave a few minutes ago. So do not forget this important detail. Now, to wrap up this chapter, I just want to remind you how the workflow goes when you're doing a Bayesian analysis. The very first step that you're going to take is that you're going to try to figure out what likelihood function you're going to choose. It could be a normal, it could be a log normal, it could be a binomial, it could be Poisson, it could be something else. So we will see other examples later on. You decide on the likelihood function. Then you decide on the priors, and you have to make sure that the priors make sense in the context of the likelihood. That's the normal log normal example I just showed you. Then write out the BRMS or stand model, right? And what I generally do and what many Bayesian researchers will then do is that they will try to understand first, before looking at the data, whether the priors make any sense at all or not. So because usually when you're working on a research problem, you have some understanding of what kind of data you expect to see, right? So the prior predictive distribution checks that I showed you earlier provide us with that information. They tell us whether we have priors that make sense. And if they don't make sense, then you change the priors to produce data that makes more sense. Once you have that step done, you fit the model to the priors that you've chosen, and then you check the posterior predictive distributions to see if those look reasonable given what you have learned from the data. So these are all diagnostic checks which help you understand the behavior of your model, right? And earlier, of course, I also showed you that you could simulate some data with known parameter values and then derive the posteriors from the model and check whether the posteriors actually contain the true values that you used for generating the data. That's also a useful way to check whether your model makes sense or not, whether it can recover the parameters or not. And so once you've fit the model, you've extracted the posteriors, you can graphically summarize them. And I always do that. I always provide a graphical summary of the posteriors. And then you can also provide summary statistics. Later on, we will also do hypothesis testing using the posterior distributions, but that comes in at a later stage. This kind of approach is conservative and safe way for you to incrementally build up your model. Of course, what I'm talking about is a situation where you're starting out working on a problem where you're fitting your very first models on the data that you're going to work on. So typically what happens to researchers is that they are working on a particular class of problems, very similar issues they are looking at over and over again over many years, even many decades, right? So I'm not saying that you have to go through this workflow every single time that you have to fit a model. Once you start working on a particular class of problems, initially it's useful to do these prior predictive, posterior predictive checks to make sure that the model behaves as you would expect. But once you're in the game and you're working repeatedly with newer and newer data and you're trying to answer more and more questions for that particular class of problems, you know that your model is identifiable. That means it can recover the parameters that produce the data, and it behaves in a way that makes sense given the context of the problem, right? So you don't have to go through these steps every single time you fit a model. This is just a general workflow for laying out the pipeline for working on a class of problems. So when I work on topics that I've been working on for 20, 25 years, I know that my models are well specified, right? Because I've used them dozens and hundreds of times. So I would go straight ahead and fit the model after deciding on the priors, which I already know would be reasonable because I know the context of the problem really well.